three-body problem involves three bodies with an initial position, mass, and velocity, and uses these values to try and map their motion in space. What's important to understand is that these three bodies interact with each other through inverse square forces. Inverse square forces are when the intensity of a force is inversely proportional to the distance squared. For example, both gravitational and electromagnetic forces are inverse square forces. To understand a three-body problem, we must first understand how a two-body problem is solved. For example, there are many classic two-body problems, the most notable probably being the Sun and the Earth. And Newton has shown that the Earth will have an elliptical orbit around the Sun. The way he derived this was by letting the Sun be standing in relation to the Earth's movement. However, when you add another body, making a three-body problem, by say adding this satellite, which itself orbits around the Earth in an elliptical pattern, we have a small problem, because no longer can we just let the Earth be relatively stable in position to the satellite. The satellite is also affected by the Sun's gravity. Therefore, we have to come up with a different way of deriving the motion of three bodies. As I mentioned before, the Sun also has an effect on the satellite. We can call this a perturbation. And here, I have three second-order differential equations which can allow us to solve for the initial position. However, it happens that this system can't be solved into a definite formula. And what I mean by unsolvable here is not in the sense that there is no solution, but that there is no definite formula. For example, we all know a quadratic in the form ax squared plus bx plus c equals 0 can be solved with a generic formula called the quadratic formula. When you're given these second-order differential equations, we can't actually solve a quadratic formula like we had here. Another way we can try and map these orbits of three or more body problems is by looking at them and then deriving something about them. For example, when we have one large body that has several smaller bodies around it, we can figure out that the ratio of the orbits are often in common small fractions, like 1/2, 1/3, or 2/3 relative to each other. For example, Jupiter has three moons that revolve around it in a 1:4:2 ratio, and these moons are Io, Ganymede, and Europa, respectively. These sorts of patterns can help us identify orbits that we might not otherwise be able to understand. Let's consider another three-body problem that's fairly practical. We have the Sun, the Earth, and a spaceship leaving Earth. So this is, in fact, a three-body problem where we know the masses, and we know the initial velocity and the initial position. So then, it's actually, theoretically, from our previous equation, it would be impossible to derive the function for the position of time for the spaceship. However, we can use a little trick where we let the mass of the spaceship be 0. Because relative to the Earth and the Sun, the mass of this spaceship is negligible. From that, we can derive a position function with respect to time for the spaceship, which is very, very useful when determining paths for lunar travel. Scientists have also helped us by deriving certain situations where, in fact, these orbits can be derived using these differential equations. For example, in 1769, Euler was able to show that if all the initial starting points are collinear throughout their motion, these bodies will be in elliptical orbits. In 1772, Lagrange also showed that if the three bodies are always at the vertices of an equilateral triangle, their motions will also be in elliptical orbits.